All right, let's get into it. Today, we're diving into one of the biggest, most mind-bending ideas in all of science, string theory. This is pretty much the ultimate quest, a search for a single, beautiful description of everything in the cosmos, from the tiniest particle to the entire universe.
So to really get why we even need something like string theory, we have to start with the problem it's trying to solve. And it's a huge one, a deep conflict that sits right at the heart of physics today. On one side of this divide, you've got Einstein's absolute masterpiece, general relativity. This is the theory that describes the universe on the grandest scales. The beautiful cosmic dance of planets, stars, and galaxies. It works perfectly. Then, on the other side, we have quantum mechanics. And this is the other half of the story. It's this theory that's it's bizarre, it's counterintuitive, but it is brilliant. It flawlessly describes the world of the very, very small. Atoms, electrons, all that stuff. And here's where things just break. These two theories are like oil and water. When you try to describe something that's both super heavy and super small, think the center of a black hole, the math just goes haywire. It spits out nonsense answers, these impossible infinities. It's a sign that something is deeply wrong with our understanding. So what's the fix? How do you possibly bridge that gap? Well, this brings us to the central idea of string theory, which puts forward a solution that is, it's radical, and a lot of people would say really beautiful. Basically, the theory just completely flips the script on what we thought a particle was. It says, forget about tiny little dots. At the most fundamental level, everything you see, everything in the universe, is made of these impossibly tiny, vibrating, one-dimensional strings of pure energy. And this is where it gets really cool. Think of the universe as like a giant cosmic guitar. A string vibrating one way gives you an electron. It vibrates a different way, and boom, you get a photon. A different vibration still, and you get a quark. All the different particles are just different notes being played on these fundamental strings.
Okay, so remember that problem we talked about? The infinities? In our old way of thinking, particles were points. And when these points interact, that interaction happens at a single, infinitely small location in space. And it's that infinitely small part that causes all the mathematical trouble when you try to include gravity.
And this is the solution. It's so elegant, really. Because strings aren't points. They have a little bit of length. Their interactions get smeared out over a tiny little area. And just by doing that, by smoothing things out, those nasty infinities that were breaking physics, they just dissolve. Problem solved.
Okay, but this is the real kicker. The thing that made physicists just stop in their tracks. It turns out one of the notes a string can play just happens to have the exact properties of the graviton, the long-hoped-for quantum particle of gravity. So gravity isn't something you have to force into the theory. It just pops out of the math, all on its own.
So this one simple idea, it has these absolutely wild consequences. For the theory to actually work without some major inconsistencies, it needed an upgrade, a powerful idea called supersymmetry. And that addition is what led to maybe the most famous and mind-bending prediction of all, that our universe is a whole lot bigger than it looks.
Yeah, for the mass to hold together, for this superstring theory not to fall apart, our universe can't just have the 4 dimensions we know and love. It has to have 10 space-time dimensions. Which, leads to the question that I'm sure is on your mind right now. If there are 6 more dimensions of space, where are they? I'm pretty sure I would have noticed. The idea is they're hidden from us. They're curled up or compactified into a space so incredibly tiny that we could never, ever see them. Think of a garden hose. From far away, it just looks like a one-dimensional line. But for an ant walking on it, there's a whole other dimension, the circular part it can walk around. These extra dimensions are like that, just on a microscopic scale. And we're not talking about simple little circles either. These are thought to be incredibly complex, twisted up 6-dimensional shapes called Calabi-Yau manifolds. And the exact shape, all the twists, turns, and holes in these hidden dimensions, that's what determines the physics of our universe. It dictates the very laws of nature that we observe. Okay, so at this point, you're probably thinking, this is some really cool math, but does it actually do anything? Can it make a real prediction? Well, let's look at one of string theory's biggest wins, solving a huge puzzle about black holes.
For years, physicists had this famous formula from Stephen Hawking that described the entropy of a black hole, but nobody had a clue why it worked. It was like having the answer to a math problem without showing your work. Then, in 1995, two physicists used string theory to actually count all the tiny ways a black hole can be formed. And when they did the math, they got the exact same answer as Hawking's formula. It was a stunning success.
That was a huge deal. It really helped kick off what's called the second superstring revolution. And scientists realized that 5 different string theories were all just different sides of the same coin, a deeper, 11-dimensional thing called M-theory. It was this incredible moment of unification, but it also opened up a whole new can of worms.
See, it turns out there isn't just one way to curl up those extra dimensions. There are a lot of ways, a truly mind-boggling number. By some estimates, something like 10 to the power of 500 possible shapes those dimensions could take.
And that right there is what they call the string landscape problem. Each of those shapes creates a different possible universe with different laws of physics. So if there are that many possible universes, how do you ever use the theory to predict why our universe is the way it is? It's a huge problem.
This is the core of the criticism, summed up really well by the physicist Peter Voigt. If your theory allows for almost any universe imaginable, then does it really predict anything at all about our specific universe?
But what if that's not a bug? What if it's a feature? Proponents have this really fascinating, kind of wild idea. Maybe all of those universes actually exist, and we just happen to live in the one that has the right physical laws to allow for things like stars, planets, and us.
And that's where we are today, really, caught in this incredible tension. String theory gives us this beautiful picture. It solves some major problems, but it's also given us this landscape of possibilities that's so vast, it's hard to know what to do with. Which leaves us with the big question. Is string theory a true glimpse into the hidden architecture of everything? Or is it an incredibly elegant piece of mathematics that might just be untestable? The quest for an answer continues.